So in this section, we will take a look at the concept of concavity and the second derivative, how these two are related. And in general, we will take a look at the second derivative and see what does it say about the function f. So first, we want to define this idea of concavity. Now consider the following two graphs. This function here, which is a graph like this, and another graph which is like this. So these are actually two functions which are both increasing, but they're increasing in a slightly different way. If we look at the first function here and we draw the tangent line, we notice that the tangent line is always below the graph. So the tangent line here is below the graph of the function. This is a function, obviously, f, say, and this is a function g. They are both increasing, but in a different way. Now, the first example where the tangent line is below the graph, this kind of function is basically said to be concave up or upwards, but we will use just concave up. On the other hand, if we look at this graph here, you can see that the tangent lines are always above. So tangent line above the graph. In this case, we say that basically the graph is concave down. Okay, now that we know what concave means, the question is, how do we find where is a function concave up and where is it concave down? Well, there is a really nice test which involves the second derivative. And this test says the following. If the second derivative of a function is greater than 0 for all x's in a certain interval I, then in that interval the graph of f is concave up. So what we're saying then is that if the second derivative is positive in a certain interval I, then in that interval the function will be concave up. Now, part B is of course similar. If the second derivative, on the other hand, is negative for all x's in an interval I, then the graph of the function in that interval, the graph of f is going to be concave down on the interval I. So, second derivative negative, that means our function will be concave downward on the interval I. At this point, I want to mention the idea of inflection point of a graph. An inflection point is a point where the graph changes from being concave down to being concave up like this. So a point here is the inflection point. So here in this region the graph is concave down, and in this region the graph is concave up. Then this point where the change happens is called an inflection point. Of course, according to the test we just mentioned, in this region the second derivative will be negative, and in this region the second derivative will be positive. Of course, the graph can also go on to do things like this. Then in this case, this point is another inflection point. So a graph can have several inflection points. Okay, so we will now take a look at a few examples. So here is a function f defined on the set of all real numbers, and I want to determine where is the graph of this function concave up, where is it concave down, and where is the inflection point. This information is actually important if we want to graph this function in a kind of a precise way. So let's see then, how do we solve this question? Of course, all the information will come from the second derivative, so I will differentiate the function twice. The first derivative will be 4x power 3 minus 9x squared plus 4x plus 1, and then the second derivative is going to be 12x squared minus 18x plus 4. Because I want to determine where is the function concave up, that means I want to know where is the second derivative positive and where is it negative, to find where is the function concave down. Therefore, really what I want to do is first solve f double dash equal to 0. So find where is this second derivative equal to 0. So this is a quadratic function. It's easy to find its solutions. x1 equal to 1.3, so that's the first solution, and a second solution is 0.27, like this. Now what I do here is, there are different ways now of proceeding, but I like to make a table to study the sign of the second derivative. So what I will do then is make a small table like this, where I put the domain of the function, which is from minus infinity to infinity, and then I will put the second derivative here, and then I will put the function f here. Now, the second derivative is 0 at 0.27. It's also 0 at 1.23, so I put these two numbers here. So at those 2 points, our second derivative is 0. Now, we need to look at the sign of the second derivative in these three intervals. To see the sign of the second derivative in the first interval, we can choose x equal to 0, and at 0, the second derivative. So I need to go into this function here. The second derivative at 0 is actually 4, so it's a positive number. And between 0.27 and 1.23, you can take 1 and substitute again in the second derivative. You will get a negative number. And finally, from 1.23 to infinity, you could take 2 and check that in this case, the second derivative is positive. According to this table, our function will be concave up here in this interval because its second derivative is positive. So concave up. And then the second derivative becomes negative in this interval. So in this interval, the function will be concave down. And finally, from 1.3 to infinity, the second derivative is positive. So our function, or its graph, is going to be concave up. Also, I can say from this table that there is an inflection point here, because at that point the graph changes from concave up, concave down. So there is an inflection point here, and there is also a second inflection point at x equal 1.3. So the conclusion of all of this is that, number one, f is concave up on the interval minus infinity to 0.27 union 1.23 to infinity. F, or its graph, is concave down on the interval 0.27 to 1.3, and there are two inflection points. There are two, so the graph has two inflection points. At x equal 0.27 and another one at x equal 1.3, like this. Okay, so let's have a look at the second example. This time we're considering a function which is x squared ln x, and we want to see where is the graph of this function concave up, where is it concave down, and find the inflection points. Okay, we will of course use the same method. We need to differentiate twice the function. So the solution will be like this. So f dash first, which is, we're going to use the product rule here. I just want to write it here. Remember, u times v, when you want to differentiate this, it's u dash v plus u v dash. So that's the rule we're going to use for differentiating this function f here. So this is the u and this is the v. So u dash is of course 2x and then ln x plus x squared, derivative of ln, which is 1 over x, like this. So the first derivative then, I will simplify it a bit before finding the second derivative. X squared multiplied by 1 over x is just x. And then we differentiate again. Again, I need to use the product rule, u, v. So it's going to be 2 ln x plus 2x multiplied by 1 over x plus the derivative of x, which is 1. So in the end, the second derivative of the function will be 2 ln x plus, of course, this x and this x will go. So this will give us 2 plus 1, 3. This is the second derivative. Next step now is to solve this second derivative equal to 0. That means 2 ln x plus 3 equal to 0. That means ln x is minus 3 over 2. And by putting exponential function on both sides, we will get the answer to this as x equal e minus 3 over 2. So that's the value of x, which makes the second derivative equal to 0. Now we're going to put this value in a table where first we put the domain of the function f. F, I remind you, is the function x squared ln x. Because of the ln here, its domain is only from 0 to infinity. Now we put the second derivative and we put our function f here. Now the second derivative is 0, when x is e to the power of minus 3 over 2, so 0 there. Now we are interested in knowing the sign of the second derivative in these two intervals. Here we could put 0.2 and substitute in the second derivative. We will see that we will get a negative number, and we could take 1 here, substitute in the second derivative, and we will get a positive number. This is telling us that the function is concave down, like this, in this interval. So concave down on the interval 0 to e minus 3 over 2. And our function is concave up on the interval e minus 3 over 2 to infinity, and it has an inflection point at x equal to e minus 3 over 2. I will now finish this section with the following question. Find the intervals of concavity So where is the function concave up? Where is it concave down? The intervals of concavity and the inflection points of the following two functions. A f of x is x to the power of 4 minus 4 x to the power of 3. And the second function to have a look at is x ln x minus x squared.